We hear all the time about these incredible, mind-bending AI models and their complex algorithms. But behind every single one of them, there's this unsung hero, the real MVP, the data. Today, we're going to pull back the curtain on the critical and often totally invisible work of data pre-processing. This is the journey that transforms raw, messy, real-world information into the high-quality fuel that actually powers machine learning. So let's follow the data on its trip from total chaos to crystal clarity.
And really, this says it all. This is the core idea. You can have the most brilliant, sophisticated algorithm in the world, but if you feed it garbage data, you are absolutely going to get garbage results. It's that simple. The quality of your data sets the absolute upper limit, the ceiling, for how well your model can ever hope to perform. It's the foundation for everything that comes after.
So, here's our roadmap for this explainer. We're going to follow the data's entire journey, from start to finish. First, we'll dig into why that data quality ceiling is such a big deal. Then, we'll get our hands dirty cleaning up the raw mess. From there, we'll put on our sculptor hats, shaping that clean data into smart, useful features. And finally, we'll see how in the world you do all of this when you're dealing with data at a truly massive scale.
All right, our first stop, data cleaning. This is that essential and, let's be honest, sometimes tedious work of bringing some kind of order to the chaos. Because let me tell you, real-world information is almost never clean and perfect. One of the first problems you almost always run into is missing data. And to solve it, you can't just fill in the blanks. You have to be a detective. You have to understand the motive. So you have to ask yourself, why is this data missing in the first place? Because the answer to that question is going to dictate your entire strategy.
Sometimes the reason is simple, right? A sensor's battery dies, someone forgets to fill out a form field. That's just random noise. For that, maybe we just fill in the average value and call it a day. But sometimes the reason it's missing is the most important part. Imagine a survey where high-income earners are way less likely to report their income. Well, in that case, the fact that the data is missing is the signal. You don't want to just fill it in. You need to tell the model, hey, pay attention, this was left blank for a reason. That distinction is absolutely crucial.
Okay, so we've handled the gaps, but what about when the data we do have is just incredibly unbalanced? Think about fraud detection, for example. Maybe 99.9% of transactions are totally normal, and a tiny fraction are fraudulent. Well, a lazy model could just predict not fraud every single time and be 99.9% accurate, and also be completely useless.
So how do we fix this? Well, there's this really clever technique called SMOTE. Instead of just copying the few fraud examples we have over and over again, which can lead to problems, SMOTE actually manufactures new, totally believable examples. It picks a fraud case, finds its closest neighbors that are also fraud cases, and then it creates a brand new synthetic data point somewhere on the line connecting them. It's a pretty brilliant way to intelligently rebalance our data set without just duplicating the same old information. All right, with our data all cleaned up, we can move to the next phase, feature engineering. Now, if data cleaning was about tidying up, this is about artistry. It's like being a sculptor, taking that raw material and transforming it to reveal the hidden patterns that our algorithms can actually understand and learn from. A huge part of this is scaling. Think about it. Some algorithms can get really thrown off if one feature is measured in dollars, going up to millions, and another is just a person's age. This slide shows the different tools for the job. Normalization squeezes everything into a range between 0 and 1, great for things like neural networks. Standardization reshapes your data so its average is 0, perfect for linear models. And what if your data has a few crazy, wild outliers that would totally skew the average? That's where robust scaling comes in. It uses the median, the middle value, so it's not affected by those extreme points throwing everything off.
Next up, we have to turn words into numbers our models can use. A really common way is one-hot encoding. It basically creates a new yes-no column for every single category. But if you have thousands of different zip codes, you suddenly have thousands of new columns, which can totally cripple your model. The alternative, label encoding, just assigns a number. Red is 1, blue is 2. The risk there is that your model might learn a false relationship, thinking that blue is somehow mathematically greater than red, which, of course, is meaningless. It's all about picking the right tool for your specific data.
Sometimes we have the exact opposite problem. Way too many features, too much information. Dimensionality reduction helps us compress all that information down to the essentials. PCA is a classic linear workhorse that finds the directions with the most information. T-SNE is a nonlinear technique that's absolutely fantastic for visualizing clusters in your data, but, and this is a big but, it's for visualization only, And then you have these cool neural network approaches called autoencoders, which learn to compress and then reconstruct the data, making them great for finding complex, nonlinear patterns.
Okay, look, all of these techniques are great, but what happens when your dataset is so enormous, so mind-bogglingly huge, that it can't possibly fit on your laptop or even on one massive server? Well, this is where we enter the world of big data and distributed processing.
To handle data at this kind of scale, you need a totally different class of tool. And in the world of big data, the undisputed champion is a framework called Spark. We're going to look at this popular Python library, PySpark, which is the absolute go-to for wrangling massive datasets across a whole cluster of machines all working together in concert. So inside Spark, you've got two main ways of thinking about your data. The original was something called an RDD, but the real game changer is the data frame. It organizes your data into a nice, structured table with named columns just like you're used to. But the real magic is what's under the hood, the Catalyst Optimizer. This thing is like a genius engine that analyzes the code you write and figures out the absolute fastest, most efficient way to execute it.
So how does that optimizer work its magic? Well, Spark has a secret weapon. I like to call it strategic procrastination. It basically never does any work until it absolutely has to. The official term for this is lazy evaluation. When you tell Spark, hey, filter this data, then join it with this other table, it doesn't actually do anything. Nope. Instead, it just adds those steps to a blueprint, a plan of action. This plan is called a directed acyclic graph, or a DAG for short. Operations like filter, join, or select are called transformations. Think of them like steps in a recipe. You're just writing down what you want to do. You're building that optimized plan, but you haven't even turned the oven on yet. No computation is happening at all.
The actual work only starts when you ask for a final result. Operations like count, which asks how many rows are there, or write, which saves the result to a file, these are called actions. An action is the command that tells Spark, okay, look at the entire recipe you've planned out, and now go. Execute it in the most efficient way you can.
One last super important concept in Spark is managing how your data is split up across all those machines. Let's say you just filtered out 90% of your data. You don't need it spread across 1,000 tiny pieces anymore. Coalesce is a cheap way to merge those pieces down without a lot of fuss. Repartition, on the other hand, is more powerful. It can increase or decrease the partitions, but it requires a full shuffle, and you want to avoid that if you can. Think of a shuffle as having to collect, sort, and redeal every single piece of data across your entire network. It's a massive data transfer, and that is often the single biggest bottleneck in any big data job.
And this brings us right back to where we started, to our central theme. After seeing this whole journey, it becomes pretty clear that all of this unseen work, it really is the most important step of them all.
Just look at this number. In so many real-world machine learning projects, over 80% of the total time and effort is spent right here, in data preparation. Not on designing some fancy, complex neural network, but on cleaning, shaping, and just wrestling the data into a usable state.
So, from handling those mysterious missing values, to intelligently rebalancing our data, to sculpting new features, and doing it all at a massive scale with tools like Spark, every single step we've talked about today is about building a strong foundation. The quality of this work literally sets the stage and defines the potential for everything that follows.
And that leaves us with one last thing to think about. In the grand scheme of an AI project's success, who really holds more power? Is it the brilliant data scientist who architects the final, elegant model? Or is it the meticulous data engineer who spends weeks down in the trenches, cleaning, preparing, and ultimately delivering the high-quality fuel that makes the entire engine run in the first place? It's something to consider. Thanks for joining me.